think it's making a video. So this is a video to Steve in BROUGH, who, has been working for quite a while on different versions of the radar experiment. And, it's, anyway, interesting history. Learning curve and all that stuff. We both had to learn some things about how radar works. And, what's feasible and what's not. And so, so I'll partly talk about that, and then paramagnetism. So I'll leave a link below to Steve's channel. I find him quite lovable, and really, I like Steve. And it's just, I could tolerate a world with more of them around. Maybe soon we'll have some evidence to present to the people who say it can't be, just to demonstrate that a lot of what you see in experiments is engineered, and the truth is being presented to you with additions. The evidence has essentially been quote mined, because they really don't do the experiments in enough variety and different ways to tease out the truth. They don't want to tease out the truth. They want to engineer a truth, and that's in an awful lot of experiments. So I guess I won't redo the thought experiment video, so the 5-minute video. I guess I'll leave a link below to that. I think that's an experiment Steve can do fairly simply, maybe a couple of different ways with regular megahertz signals and with the radar. I think it's pretty easy to do. Just put the same signal on 2 different horns and just vary their distance to a little piece of metal in between the 2 horns, and you should be able to create interference by just moving one of the horns in and out, and essentially demonstrate that the interference isn't really any photons interfering with each other. It just has to do with the fact that the signal becomes impossible for the receiver to translate as the original frequency, because it's getting hit by 2 different frequencies out of phase. It's just like a punching, if one guy is hitting somebody, right, one hit a second, and then another guy shows up and hits him from the other side, one hit a second, he's going to feel 2 hits a second. The frequency is going to be increased as far as he's concerned. Yes, the 2 sources are just ones, but it adds up. So anyway, I'm pretty confident that he'll find those results. It'll be just in my opinion, it'll be a bit of decisiveness one way or another, I suppose, in terms of if it isn't true, that there is no interference pattern, even though there's no mechanism for the interference. I mean, clearly it would show there's no mechanism for interference. The 2 waves never interact before they hit the antenna. So there's no way you could say the photons interfered with each other. And so in my opinion, clearly demonstrates the feasibility that the entire radio wave radar experiments demonstrating interference don't demonstrate interference. They just demonstrate that you can jam a radio signal. So look forward to that. So he did some more video on paramagnetism. He apparently doesn't like some of the things I've said. I guess I'll just try to restate them, because I don't think we have a fundamental disagreement. So it's this idea of what's causing effects, magnetic effects in paramagnetic versus diamagnetic materials, and Lenz's law, which is the thing saying that basically when a magnet's moving, it's going to create a field that's going to repel the existing field. Now I'm arguing it's not really. He even concedes, I've used the word mirror before, that all you're doing is moving the pressure. So you can't say if you're pushing pressure onto something because you're pressurized, and so you're pushing it. You're under pressure, and you're going to relieve your pressure in a way onto something else. Well, clearly you're going to pressurize it. So now there's going to be a conflict between your pressure. There's nowhere for the pressure to go, so to speak. So you're only going to increase pressure because now the other guy has pressure and he's going to throw it back at you. And then you're going to throw the pressure back at him and he's going to throw it back at you. So the pressure's not going somewhere else. And so it does work that way. But the problem is that paramagnetic and ferromagnetic materials behave very differently in the sense that there's two effects for a ferromagnetic material. The paramagnetic effect is only affected by moving magnetic fields. So if the field isn't moving, the conductor gets rid of it. But with ferromagnetic materials, because they already have built-in dipoles, the dipoles turn the ferromagnetic material into a magnet ahead of time. And so that magnetism is much stronger than the paramagnetic effect. So you can't measure the paramagnetic effect because the ferromagnetic effect is 1,000 times stronger. So it overwhelms the paramagnetic effect of, say, something like iron. So you'll never see that iron's paramagnetic because it's ferromagnetic. The things aren't in conflict. It just means that certain materials behave certain ways because they can be charged in a dipole way versus being charged in a monopole way. So that would be my argument, is that the paramagnetic materials react as dipoles. That is, they interact with the field individually. So if the red part or the south part of the magnet affects them, then they have south part, but they're not creating north parts with it. They're just reacting to the south part, and they create a mirror to the south part. And the north part creates a mirror to the north part. But there's no built-in dipoles. There's no dipoles turning or doing anything. It's really just charge. So you're just creating, you can have dipole of charge that you're pushing onto something because you're pushing the whole magnet onto it. But it's reacting to the individual poles of the magnet. It's not reacting to the dipole. There's no domains turning. There's no atoms turning. So it's just getting pressurized. It's creating a current. Where in magnetism, as stated, you're not only creating a magnetic reaction, which is going to end up being attractive, the strong magnetic reaction, but you're also creating the current, the resisting current that's going to move through the iron. So, but there's like I said, there's no way to see one of them because the other one's so much stronger. Yeah, so that's probably enough on that. So I guess I don't know if I need to draw anything, but I guess I'll throw it in just for fun. So anyway, he did some experiments with it. He did an experiment with a raisin, okay, and the raisin resists. But the thing to understand, well, the raisin sticks. So, but that's because the raisin it's not paramagnetic, it's ferromagnetic. The reason why raisins work is they have a lot of iron in them, so they really are magnetizing. So that's why they stick to the magnet. So I guess I could show some of that. The magnets, it stick. It always, the raisin, let's see if there's a good video of it. Well, let's just play a little bit of it.
There we go.
So there's the raisin.
So the magnet's pushing it that way.
So he's pushing the magnet, the raisin. So
Push
that's
it back
the
again.
magnet.
I'll keep it going. So you just keep pushing it because it's diamagnetic. Yeah. I'd say about 3 or 4 millimeters away from it, really. Always going to be somebody saying, yeah, it's draft. Yeah, the magnet can, but the steel couldn't do that, could it?
So I think that's a raisin. So, pretty sure. So that's what he's using here.
So it's a very, very, very big force. I think it's about 100,000 times smaller than ferromagnetism. A better demonstration, perhaps. So try to push it that way. Can the camera see it? Yeah. There we go. So the magnet is pushing it that way.
The question might be is if you touched it with a magnet, and then it would then have the same magnetic. So that's sort of the trick, right? I mean, if you touch it, you can magnetize it even better. And so then the raisin's already been magnetized. So it'd be interesting to get on the other side of the magnet and see if you push it the opposite way. But I guess
Push it back again.
the momentum will end up being too strong and it'll end up hitting the magnet again. Well, anyway, I won't argue with what raisins are. So maybe they're just paramagnetic. Maybe the iron doesn't really matter. It's not a significant player. Well, you have to explain what is, right? I mean, why something's paramagnetic means that it has to, to have any of these effects, it has to be a certain amount of conductivity, plus, I guess that's it. You just have to be a conductor, which means you have atoms that can be pressurized. That would be my argument. They can be pressurized or depressurized. That is, you can force the electrons in or you force the electrons out, which changes the field it projects. As I've explained before, if I'm a proton, my head, and I put this pen really close to the camera, from your perspective, I'm not very proton strong now. I'm very weak proton. But if I put it close to me, I'm very strong proton and very weak electron. And that's all that's really happening. All right. So he does it with, pushing different things. So now he's pushing it with a dipole magnet. And so he tries other little bits of metal to make the point that some stick and then some repel the movement. And obviously the trick with iron things is that the fact that they become sympathetically magnetic, the pole that's going to be attracted is the pole that's going to be attracted. So they end up moving in a way that creates a strong attraction. So even though there might be some movement in the magnet creating pressure to create force, the fact that the domains are in the wrong position, they're attractive, means that you can't overwhelm them with the Lenz's law current. So the magnetism is much, much stronger than the paramagnetic or diamagnetic effect. The ferromagnetic magnetic attraction
Lenz's law break.
Fundamentally wins the battle. Unless you're doing something like using a steel core with an induction, inducing a magnetic field in a steel core or something, or that's all Lenz's law in a sense. Well, it really isn't. No, it really isn't. That's just aligning the domains again. Because if the domains stay, you have a permanent magnet. So, and it's a strong permanent magnet. And it's just the fact that the domains don't necessarily stay in steel. You have to keep nudging them to align. They don't want to align just because of heat in the environment. So if you make it cold enough, then the magnet will stay aligned. Alright, so I don't know if I need to beat that subject to death. But I don't think there's an actual current in Lenz's law, because that would relieve the pressure. That would break the mirror. So the idea is the atoms get pressurized by movement. And so when you stop moving, that's when the pressure escapes it, because it's a conductor. So it's actually when things stop is when the current moves. And when things are moving is when there might be current moving, but the point is it keeps being created. So the mirror only exists because it takes time for the current to escape the pressure. So the mirror only exists for as long as the movement is happening. And as soon as you stop moving the thing that's causing the mirror reflection. So it's like thinking if something's moving towards me, I turn silver. And then as soon as something stops, the silver disappears. And then when it starts moving away, then the silver's again. And it's, and we're just saying that the silver is either red or blue, depending on whether I'm reflecting the north side of the magnet or the south side. So the silver has a tinge to it, blue or red. And so if something moves away from me, I turn blue silver. If it's moving towards me, I turn red silver, depending on what thing is moving towards me. So again, it just depends. But I'm arguing that they're individual atoms and they're not dipoles. So in paramagnetic material, there's no dipoles. There's just mirrors to whatever force hits the atom. So if more green force hits it, it turns green. If more red force hits it, it turns red. And it's that simple. No dipoles on purpose. No true magnetism. It's really a charge. So paramagnetic material are essentially being charged. Ferromagnetic are being turned into magnets first, and then the paramagnetic effect, the Lenz's law effect, is smaller than the magnetic effect, which doesn't require any movement. So all I have to do is put the magnet anywhere near the steel, and it's already turned into a magnet. So it's like the iron filings don't need the you can have iron filings standing straight up on the piece of paper and nothing's moving. You just leave the magnet there, leave the iron filings there, and the iron filings are defying gravity, right? Clearly. I mean, they can be in weird angles like this. They're defying gravity. So there's clearly a force acting on them, right? To keep them defying gravity. They don't need to be moving. So it's just because they've been turned into a magnet, and now they're levitating magnetically. But that force is 1,000 times stronger than the moving force, the Lenz's law force, the force being the mirror force. The mirror force is pretty weak because the magnet's not very big. It doesn't affect a zillion atoms and all that kind of stuff. It just doesn't have enough of an effect. It's a surface phenomenon, essentially. The Lenz's law. It's essentially a surface phenomenon. That's kind of like why say if you're going to make a maglev train or something, you have to have a big sheet of aluminum. Because you need more surface area. It's a surface phenomenon. Yeah, so that's probably enough. I probably don't need to draw. But I can. I'll just show you. See? Yeah, it's pretty. Higher resolution. Nice. Alright, anyway. So it does, this does work much better. Like I said, on the old computer, which is irritating. But anyway, so I don't think there's anything else to say. So, so yes, I guess I should say that Steve, yeah, I'll draw a picture of it real quick. No, what I'll do is, yeah, a better thing to do is I have a link to this old video. Okay, so this is pretty interesting. So we'll play this. Yeah, that's right. All right, so this is, I'll leave a third link to this video. So this is this old, whatever, 50s video. So they're doing this with with a regular radio, the regular antennas. Okay, they have the antennas this way, I think, horizontal. Well, anyway, and they're detecting the radio signal 40 meters away, doing basically the radar experiment with a megahertz, an AM kind of signal. And so that's sort of interesting. But again, they're measuring the tone. So the meter's not measuring the actual signal hitting the antenna. It's not measuring the electricity created in the antenna, the total electricity. And if it was doing that, I would argue it wouldn't see any deflection at all. The total energy hitting the antenna would always be the same. All it's measuring is what it can receive at a specific frequency. So, but the interesting part is that he has the radar experiment here, and they were so close to doing this experiment right. And it's just kind of disappointing they didn't do it right.
Microwaves in a tube called a klystron. Here's one. The microwaves come out from this antenna. We pump electric charge or current up and down this antenna, and the accelerated charge sends out the waves.
Yeah, well, see, what he's not saying it, but it's a little more complicated than that. You send in one signal to create a initiation frequency, and then you put in a resonating chamber, and it amplifies the frequency tremendously. So it's like you put a little frequency in, and you get a much higher frequency out.
We've got the same klystron in this metal can.
I believe that's how it works anyway. But look at all these tubes they're putting the radar through, which is kind of funny.
The accelerated charges on the antenna start an electromagnetic wave down this pipe.
Yeah, there's no electromagnetic wave. It's just photons.
The wave reaches this point and splits and arrives at these 2 points with identical phase. We then feed them through these 2 horns out into space.
All right, so he basically has those 2 horns, but this experiment would be better to do without that. But this is exactly how he's going to be able to do the experiment now. Because see, the problem was he couldn't receive the double signal. So I kept pointing out how what you're really going to be wanting to look for is that the on-off pattern will be exactly reversed at double the frequency. At double the frequency, at the dead spaces, you'll get a signal, and at the spaces where it's supposed to be constructive interference, you'll get nothing. So it'll be exactly the opposite signal.
The purpose of the horns is to minimize reflections, which are caused when we make the transition between the pipe and the space.
Yeah, well, that's not exactly true either. It's to minimize the fact that, yes, the radar, if you just used a straight antenna, it bounces off all kinds of stuff. So it's going to interfere with any kind of a ton of reflections are going to interfere, right? They're going to jam your signal. They're going to be out of phase. It's going to cause out of phase interference to your receiving antenna. That's why your radar has to be exclusive. It has to eliminate reflections or it can't see anything.
The 2 horns in this experiment will act just like the double slit did in the optics.
Right, so this is a statement where clearly it's not just like the 2 horns are not a single photon. So when he made this video, they already had done this single photon experiment. They already knew that in the light experiment it was single photons that are doing all of this wave calculus. And there's no argument that 2 different photons are interacting and creating the pattern. Nobody argues that that's what's happening in light anymore, because that wouldn't make any sense, because then you'd have 2 different kinds of wave interference.
Here we have a detector which is sensitive to the resultant electric field tangent to it.
So it's just an antenna as long as essentially 3 plus centimeters, as long as the signal wavelength. I think you could just use a longer antenna, it would work too, but anyway. So he's just using basically a piece of some sort of metal that probably makes a good antenna. I don't know whether there's a specific kind, but this is really the best way to receive it. So you would be receiving just the energy, but you can see the speaker right there again, and the meter again. So again, what they're doing, instead of just receiving the energy and measuring how much electricity is in that piece of wire, see, they should just measure the wire and just say, okay, here's the noise level. And then they turn on the radar and it go up. The noise level goes up because you're introducing a whole bunch of more photons. And they'll be telling you, well, this is the noise signal, the base, and everything above that's the radar. And so then you could just see the needle would go to, say, 3 or 2. That would be the base. You turn the radar on, and it goes to 5. Well, now you know that's the radar signal. It's the 5. 3 is the base, 5's the radar. And so then you just measure you're actually receiving energy on that probe. So if they just measured the voltage on the probe, problem solved. Then they would know there's no interference, because they would see the energy doesn't change. There is no on-off to the energy. There's only on-off to what they receive. I mean, what they can interpret. The signal, the energy that's in the piece of the antenna is isn't what they can see. Just as right, anytime your radio is tuned to a station, it's not seeing all the other stations. It's not seeing all the other stuff that's hitting the antenna. So as soon as you tune it to a specific frequency, you're basically saying, I don't care what other energy there is. And in this case, again, the simple argument is if you're throwing two frequencies in, you're creating a new frequency. And you have to look for it to find it.
We're going to move the detector back and forth through space this way, thus sampling the total
Right, so the argument I'm making, just take the two dishes and say one's on that side and one's on this side of that little nail, have them shoot right at each other, and you'll see that as you move one of them in and out, you'll create in phase, out of phase, in phase. Every 3 centimeters you'll have an in phase and out of phase event. So every 1.5 centimeters that you move the dish, you'll have a signal on, signal off, signal on, signal off.
electric field resulting from both these horns at each point in space. The output of the detector will be fed to this meter.
So the only trick will be is to avoid any reflections. So the two emitting horns shouldn't have anything behind them, so any extra energy is dissipated, and so you don't have any reflections screwing things up.
Now let's do the experiment. As I move the detector this way, across the incoming wave.
So again, you hear the tone, and the needle is, they're just measuring the carried audio signal. So you first have to tune to the frequency of the radar to get the audio signal. And if you're not, if you can't tune the signal because it's interfering with each other, it's doing this, yeah, quite obviously you'll have the appearance of a dead spot. It's not a real dead spot. There's still energy hitting the antenna. All right, I've said that 14,000 times. I think it's clear enough. So anyway, yeah, so some good videos. I mean, this is a really good one. I mean, it has all 3 experiments, really. Why do they keep doing that next thing? Yeah, so it has the photon. It's a good old video. I mean, you know, and it's using the photo multiplier here. I believe it uses one here. You know, and it points out how you have to put it in ice and all that kind of crap. So, quite useful. Oh, and this wave thing was quite interesting. You know, to explain how reflections and refractions off of surfaces. And again, this is the whole point. The 2-slit experiment is all about surfaces. And so people have this idea that the only part of the surface that's changing something is when you're coming at the surface this way. And there's no physicist has thought about it enough to say, well, maybe the same effect happens when you're coming this way, because you're going through the surface transition. It's the transition between the 2 surfaces that are causing the effect. And that transition, you can go through it. You can go through the transition this way, or you can go through the transition this way. And they've never even considered what happens when you go through it this way. And that's what I say is causing the effect in the 2-slit experiment. It's just a refraction, because you're going through the surface layer. I think that's a plausible explanation for the effect. Alright, so that's probably enough. Keep it a little bit within reason. You know, I'm already 30 minutes. Alright, so till the next time and such. So links below to Steve's channel and something else I forgot already, and this video. Okay, well, hopefully I'll remember the other thing. So till next time.